Perhaps you have seen the image somewhere before. A vast sphere glowing in shades of pink and violet, drifting silently through the deep black of space. Bands of clouds curl around it in layered formations, sometimes dark like red wine, sometimes fading into a cold purple light. From a distance, it resembles an unfamiliar version of Jupiter, softer, darker, and seemingly wrapped in an atmosphere unlike anything we have encountered in the solar system. That image is often given a name that is easy to remember, the pink planet GJ 504b. But that is not what telescopes actually see. In the observational data, there is no clearly defined sphere. There are no purple cloud bands stretching from one pole to the other. There is no sharp atmospheric outline emerging from the darkness. GJ 504b appears only as a tiny point of light beside the vastly brighter glow of its host star. Without a marker showing where to look, most of us would probably glance past it without realizing that this faint speck belongs to a world larger than Jupiter. The familiar pink globe is, in fact, a scientific illustration created from data. It helps us imagine an object so distant that telescopes cannot clearly photograph its cloud layers or surface features. But that vivid appearance has also unintentionally hidden the more interesting part of the story. The most important discovery about GJ 504b is not found in the pink color our eyes can see. It lies within a very small amount of light that traveled nearly 60 light-years before reaching a human instrument. Welcome back to Night Cosmos Sleep, where we listen to the scientific stories hidden within the light of stars, distant planets, and regions of space that humanity cannot yet visit directly. In today's story, we will not attempt to descend toward GJ 504b, nor will we imagine creatures or cities hidden beneath its pink clouds. Instead, we will stay close to what telescopes have actually recorded, following the trail from a faint point in an astronomical image to chemical signatures discovered within its atmosphere. For many years, GJ 504b remained a difficult object to understand. It orbits far enough from its host star to be directly imaged, yet its light was too faint for earlier telescopes to fully read what was happening inside its atmosphere. Astronomers knew that the object was still radiating heat. They could estimate its temperature, brightness, and distance. But the composition of the surrounding gases remained like a dark room, allowing only a thin line of light to escape through the doorway. That changed when the James Webb Space Telescope turned toward the system. James Webb does not see the clouds of GJ 504b in the way a weather satellite sees clouds on Earth, nor does it enlarge the faint point into a globe where individual regions of the atmosphere can be examined. Its work is far more subtle. It gathers the extremely weak light coming from the object, separates it from the overwhelming glare of the nearby star, and spreads it into a range of different wavelengths. That band of light is called a spectrum. At first glance, a spectrum looks like nothing more than an uneven line rising and falling. Some regions are brighter, while others dip downward, as though small pieces of the light were removed as it escaped from the atmosphere. But those missing regions do not appear at random. Each type of molecule tends to absorb particular parts of the light. By studying where the spectrum becomes weaker, researchers can trace the gases present on a world they have never seen clearly. In the light from GJ 504b, James Webb detected signs of water vapor, methane, carbon monoxide, carbon dioxide, ammonia, and several other molecules. That alone was enough to produce a far richer picture of the atmosphere than anything previously known about this object. But then a problem appeared. When scientists placed the newly detected molecules into familiar atmospheric models, the simulated spectrum did not fully resemble the one James Webb had actually recorded. Some features became too strong. Certain regions of light appeared brighter or darker than the data allowed. It seemed that the atmosphere was hiding another component, something that did not reveal itself through a clear chemical fingerprint, yet quietly changed the entire amount of light escaping into space. The researchers adjusted the temperature, gravity, atmospheric composition, and the amount of movement between different layers of gas. Each change explained part of the spectrum, but mismatches still remained. Only when they added a cloud layer formed from salt compounds did the simulated spectrum begin to resemble what James Webb had truly observed. No one has directly seen those clouds. There is no photograph showing them swirling around GJ 504b. No instrument has flown through them to collect cloud particles. Their presence was recognized in a more indirect way. Without such a cloud layer, the object's light becomes extremely difficult to explain in a reasonable way. This is the paradox that makes GJ 504b so remarkable. A cloud layer that cannot be seen directly may determine how we understand the temperature, chemical composition, mass, and even the origin of the world beneath it. And the more astronomers study it, the more they realize that the name pink planet may describe only the outermost layer of a much more complicated story. GJ 504b may be more massive than early estimates suggested. It may be older. It may even lie close to the uncertain boundary between a giant gas planet and a brown dwarf, an object that is not quite a planet, but never became a true star either. Before going deeper into those salt clouds and the chemical signatures hidden within the light, however, we need to return to the image that made this world famous. Is GJ 504b really pink, as the name given to it by humans suggests? When a distant world is called a pink planet, it is easy to imagine that somewhere in space there truly exists an enormous sphere colored in shades of pink and violet, with clearly defined cloud bands curling around it like the belts of Jupiter. That image appears in many articles, videos, and science websites. An almost perfectly round globe suspended against a black background, covered in bright and dark regions colored like red wine, pale purple, and deep pink. In some illustrations, the clouds seem to stretch into broad bands. In others, they form soft, flowing patches that make GJ 504b look like a world being observed from a spacecraft passing nearby. But no spacecraft has ever traveled there, and no telescope has yet seen GJ 504b clearly as a globe with distinct cloud bands. In the actual observational data, this world is far smaller than the familiar image shown in the media. It appears only as a faint point of light beside another point that is much larger and brighter. The larger point is the star GJ 504, while the smaller one next to it is the object we call GJ 504b. Without the circles or arrows added by researchers, most viewers might not recognize which point they are supposed to find. There is no horizon, no visible shadow, and no clearly defined cloud structure. There is only a very small amount of light recorded by an instrument after traveling nearly 60 light-years. That is the true beginning of the story. GJ 504b was discovered with the Subaru telescope, a large telescope located near the summit of Mauna Kea in Hawaii. Subaru observes the sky using several different instruments, including systems designed to find extremely faint objects located close to bright stars. The name Subaru refers to a familiar star cluster in Japanese culture, but the telescope is used for far more than observing stars. One of its most difficult tasks is detecting light from planets or companion objects beyond the solar system. This is especially challenging because a star produces its own powerful light, while a planet usually reflects only a tiny fraction of that light or emits the faint heat left over from its formation. When the two objects appear close together in the sky, the star's glare can easily overwhelm the planet completely. Imagine someone standing very far from a lighthouse at night. Beside the powerful lamp is a small piece of coal glowing faintly red. Viewed on its own, the coal is not completely dark. It still produces a small amount of light, but placed beside the brilliant beam of the lighthouse, it nearly disappears. The situation with GJ 504b is similar, although the distance and contrast in brightness are far greater. To see that tiny point of light, astronomers had to reduce the influence of the star's glare, correct for the blurring and movement caused by Earth's atmosphere, and process the data with great care. After observing it several times, they confirmed that the faint point was not a distant background star that happened to lie along the same line of sight. It moved together with GJ 504, showing that the two objects truly belong to the same system. The discovery was announced in 2013. At the time, GJ 504b quickly attracted attention not only because it could be directly imaged, but also because of the color revealed in its infrared data. Infrared light is a part of the electromagnetic spectrum that the human eye cannot see directly. It lies beyond the red end of the visible range. Objects that are warmer than the space around them can emit infrared radiation even when they do not shine clearly in visible light. Telescopes can record that infrared energy, but because human eyes cannot see it, scientists must translate the data into colors that we can view on a screen. This process can sometimes lead to misunderstandings. When an astronomical image appears red, blue, or purple, we often assume that these are the actual colors a person would see if they were standing near the object. In some cases, that may be approximately true. But in many astronomical images, color also acts as a kind of language. It helps distinguish different wavelengths, temperatures, or materials that the human eye would otherwise be unable to recognize. One region may be colored red to represent a longer infrared wavelength, while another is colored blue to represent a shorter one. When several layers of data are combined, they create a clearly colored image, even though those colors may not exactly match what human eyes would see from nearby. For that reason, it would not be entirely accurate to call such astronomical images fake. The underlying data is real. The light recorded by the telescope is real. The object's position, brightness, and differences between wavelengths all come from actual observations. What humans choose is the method used to translate that invisible information into colors we can see. Rather than calling it false color, a more accurate and accessible description would be color reconstructed from infrared data. In the original observations, GJ 504b stood out in shades of red and violet when data from several wavelengths was combined. From there, the image of a deep pink world gradually became popular, while scientific artists expanded the tiny point of light into an atmospheric globe based on what was known about giant gas planets. They did not paint a rocky surface because GJ 504b was believed to be a world composed mainly of gas, with a size comparable to giant planets such as Jupiter. They added cloud bands because large atmospheres often contain motion, convection, and multiple layers of material. They chose pink and violet tones because those colors had become associated with the infrared data and with the way the object was introduced after its discovery. These illustrations are valuable because they make an object represented by only a few pixels easier to imagine, while giving the public a memorable image. If GJ 504b had been presented only as a table of numbers or a nearly invisible point of light, very few people might have paid attention to it. However, an illustration must also be understood for what it is. It is not a close-up photograph. The cloud bands in the artwork have never been resolved by a telescope as separate structures. We do not know whether GJ 504b has broad atmospheric belts like Jupiter or scattered, broken cloud regions. Nor do we know whether its clouds would truly appear pink to human eyes. Even the idea of what human eyes would see is not simple in a place like this. Human vision evolved to function beneath sunlight and inside Earth's atmosphere. On a distant world, the colors we perceived would depend on the light from the host star, the density of the atmosphere, the composition of the clouds, and the observer's location. Until those conditions are fully understood, no single color can describe the complete appearance of an entire planet. The name Pink Planet should therefore be understood more as a memorable image than as an exact description of every detail. This does not make GJ 504b any less interesting. On the contrary, it brings us closer to the way astronomy actually works. Astronomers rarely begin with a clear photograph. More often, they begin with extremely small signals, a point of light, a slight change in a star's brightness, a subtle motion, or a spectrum containing a few unusual regions. From these modest clues, they must gradually build a much larger picture. Imagine someone standing outside a house at night. The window is closed, and the curtains are nearly drawn. From the street, that person cannot see the entire room. They do not know where the furniture is placed, what color the walls are, or how many people are inside. Yet a small amount of light still escapes through a narrow opening. If the light has a warm yellow color, the observer might infer that the room is using a particular type of lamp. If the brightness changes, perhaps someone has just walked past the window. If the light contains distinctive features, it may even reveal the type of light source or the materials that absorbed part of the light before it escaped. GJ 504b is like that distant room. We cannot yet see inside, but some of its light has escaped, carrying information about the place it has just passed through. Color is the first layer of information. Brightness is the next. By measuring the light across several wavelengths, researchers can estimate the object's temperature and compare it with other planets or brown dwarfs. By separating the light in even greater detail, they can search for regions absorbed by molecules in the atmosphere. That is why the tiny point of light is more important than the pink globe in the illustration. The artwork helps guide our imagination, but the point of light contains the data needed to test whether that imagined picture is correct. For many years after its discovery, GJ 504b was studied mainly through infrared data gathered by ground-based telescopes. Scientists knew that it emitted heat, knew that it lay far from its host star, and could estimate several basic characteristics from its brightness and infrared color. But the available light still lacked enough detail to answer the most important questions. Which molecules were present in its atmosphere? Did it contain layers of clouds? Was the escaping light coming from deep within the atmosphere, or was some layer of material blocking it? And why did an object that appeared relatively cool and faint still exist at such a great distance from its star? Those questions could not be answered simply by enlarging the image. No matter how powerful the telescope, GJ 504b remains too distant to appear as a globe with clearly visible cloud bands. Astronomers needed a different approach. They had to collect as much light as possible from that tiny point, then separate it into individual wavelength regions, much like spreading a beam of light into an extremely long band of colors. Within that band, each molecule could leave its own distinctive mark. The goal was no longer to create a more beautiful image. It was to read the story contained within the light. This was also the point at which the name Pink Planet began to recede into the background. The pink color had made GJ 504b memorable, but it could not reveal how the world formed, how massive it was, or what its atmospheric layers contained. To uncover those answers, humanity needed a telescope capable of observing infrared light with far greater sensitivity, operating beyond Earth's atmosphere, and equipped with instruments delicate enough to separate the light from an extremely faint object. Nearly a decade after GJ 504b was discovered, that instrument finally began operating. If the real image showed only a tiny point of light, what made that point so unusual that the James Webb Space Telescope had to return and observe it? When GJ 504b was first announced, its story seemed relatively straightforward. There was a star with many similarities to the Sun, a companion object orbiting far beyond it, and a faint infrared point of light that appeared to be a young gas giant. Early estimates suggested that it was only a few times more massive than Jupiter. If that was correct, GJ 504b would have been among the lowest mass exoplanets ever directly imaged at the time. It also presented an appealing picture, a young, relatively cool world glowing in shades of pink and violet, orbiting a sun-like star at an enormous distance. But that mass was never measured directly on a scale. No instrument traveled close to GJ 504b to measure its gravity. Astronomers had to infer its mass by combining its brightness, temperature, and the estimated age of the star system, with models describing how giant gas planets cool over time. That made the result depend heavily on one seemingly simple question: How long has GJ 504b existed? A giant gaseous object forms in an extremely hot state. As gas and material fall into it, gravity compresses the inner layers and releases a large amount of energy. Once formation is complete, the object gradually begins to cool. Heat from the interior moves through the atmosphere and escapes into space as infrared radiation. Over time, the object becomes fainter. A young object may remain bright even if it is not especially massive, because it has not yet had enough time to lose its original heat. By contrast, if an object has existed for billions of years and still emits a significant amount of thermal energy, it usually needs to be more massive to retain that internal heat for so long. When GJ 504b was discovered, several features of its host star suggested that the system was relatively young. According to that interpretation, the companion object had not been cooling for very long. Its infrared brightness could therefore be explained by a mass only a few times greater than Jupiter's. That result supported the description of GJ 504b as a giant planet, even though its extremely wide orbit remained difficult to explain. However, determining the age of a star is not always easy. Astronomers may know, with considerable precision, how far away a star is, how hot it is, or which elements it contains, but its age often has to be inferred from several indirect clues. Its rotation rate may indicate how much the star has slowed over time. Magnetic and X-ray activity may reflect whether it is young or old. Its chemical composition and its position on a diagram of stellar evolution provide other clues. The problem is that these different indicators do not always lead to the same answer. Later studies began to suggest that GJ 504 might be much older than originally assumed. Instead of having formed during only a small fraction of the Sun's lifetime, the system may have existed for billions of years. If that is true, the interpretation of the companion object must change. A lightweight world only a few times more massive than Jupiter should have cooled considerably over such a long period. It would have become fainter than the point of light telescopes actually observe. To retain its current temperature and brightness after billions of years, GJ 504b may need to be far more massive. This is a significant change. The same point of light, at the same distance, and with nearly the same observed temperature, can shift from a few Jupiter masses to several dozen simply because the estimated age of the system changes. At first, GJ 504b was pictured as a young and relatively lightweight gas giant. Once the possibility of an older system was considered, it began to resemble a massive object near the boundary between a planet and a brown dwarf. A brown dwarf is a type of object that lies between the largest gas planets and the smallest stars. It may form from the contraction of a cloud of gas, in a process similar to the birth of a star. However, it does not have enough mass to sustain ordinary hydrogen fusion in its core. Hydrogen fusion is the process that allows stars such as the Sun to shine steadily for billions of years. Without that long-lasting source of energy, a brown dwarf radiates mainly the heat left over from its formation and gradually cools over time. The name brown dwarf may suggest a small star that appears brown, but in reality, the colors of these objects vary with their temperature and with the wavelengths used to observe them. They are also extremely faint in visible light, and are therefore often detected through their infrared radiation. What matters is not the color brown, but their intermediate position. They are too massive to be easily regarded as ordinary planets, yet not massive enough to become stars like the Sunday. In many popular explanations, a boundary of about 13 times the mass of Jupiter is often used to separate giant planets from brown dwarfs. This is close to the mass at which an object may begin burning deuterium, a heavy form of hydrogen left over from the early universe. This reaction does not last as long as ordinary hydrogen fusion inside a true star, but it has often been used as a convenient dividing line. Nature, however, does not necessarily obey the boundaries humans draw on classification charts. An object more massive than 13 Jupiters does not automatically tell us how it formed. In the same way, An object below that limit did not necessarily form like a planet. Mass is an important piece of information, but it is not the only one. We can imagine two objects with nearly identical masses, but completely different histories. The first is born inside a disk of gas and dust, orbiting a star. A solid core forms first, then attracts a large amount of gas and grows into a giant planet. The second forms when part of a gas cloud or disk collapses directly under its own gravity, more like a small star. When observed today, the two objects may have similar sizes, temperatures, and brightnesses. The main difference lies in how they were born a history that no telescope can observe directly. Astronomers therefore also examine the orbit, chemical composition, and relationship between the object and its host star. A planet formed within a disk of material may accumulate heavy elements in proportions different from those of the star. Its orbit may preserve traces of migration or interactions with other planets. A brown dwarf that formed more like a star, meanwhile, may retain a chemical composition closer to that of the original gas cloud. These clues are not always clear, but they allow the question to extend beyond a single measurement of mass. The new spectroscopic study based on James Webb data moves GJ 504b closer to the brown dwarf region. The models that best match the spectrum produce a central mass estimate of nearly 25 times the mass of Jupiter. Although the estimated range remains fairly broad, this is far higher than the few Jupiter masses reported during the early years after the discovery. If that result accurately reflects the nature of the object, GJ 504b no longer resembles a lightweight gas planet. It becomes a massive object with stronger gravity and enough capacity to retain internal heat for billions of years. This change does not mean that the early studies simply made a mistake. Science often begins with limited data. Researchers use the best observations available, select the most appropriate models, and publish both their conclusions and the remaining uncertainty. When new data becomes available, especially more detailed spectroscopy, earlier assumptions are tested again. A changing conclusion is not a sign that science has failed. It shows that the method is working as intended. The picture is revised as the evidence becomes clearer. In the case of GJ 504b, the change involves far more than a single number. It transforms the entire way we imagine this object. At first, it was a young, pink, lightweight planet in an extremely wide orbit. Later, it became a world that may be much older, far more massive, and more closely related to cool brown dwarfs. Today, it still does not belong completely to either side. Its newly estimated mass makes it resemble a brown dwarf, but its position around a sun-like star and certain signs in its composition may still point toward a planet-like formation process. That is why articles and research Jambe always describe it in the same way. The media often uses the phrase pink planet because it is brief, memorable, and connected to the history of the discovery. Some articles continue to call GJ 504b an exoplanet because it was discovered as a directly imaged companion orbiting a star. More cautious studies may instead use phrases such as planetary mass companion, substellar object, or simply GJ 504b, avoiding a premature conclusion about its sedentary mass companion. Classification: a substellar object is an object with less mass than is required to become a star, capable of sustaining stable hydrogen fusion. This group can include both giant gas planets and brown dwarfs. The term may sound less appealing than pink planet, but it more accurately reflects the uncertainty that remains. One remarkable detail is that the object's outer size does not resolve the problem easily. Jupiter, an object 10 times more massive than Jupiter, and a brown dwarf dozens of times more massive than Jupiter, may all have radii that are not dramatically different. As mass increases, stronger gravity compresses the material inside, preventing the size from increasing in direct proportion. An object that is far more massive may still be only about as large as Jupiter. Seeing a globe with a planet-like size, therefore, does not mean its mass resembles that of a familiar planet. Color does not provide the answer either. A gas planet and a brown dwarf with similar temperatures may contain many of the same atmospheric molecules, including water vapor, methane, carbon monoxide, and ammonia. Their clouds may also form from similar compounds. Spectroscopy helps determine composition, temperature, and gravity. But to infer the object's origin, researchers must combine several different clues. The wide orbit of GJ 504b makes the story even more complicated. If it formed like a planet, models must explain how such a large object could gather enough material at such a great distance from the star. It may have formed closer in and later been pushed outward, or the disk surrounding GJ 504 may once have been large and massive enough to create a giant world in its distant outer regions. If it formed like a brown dwarf, the wide separation may be easier to explain. But in that case, its chemical composition would be expected to resemble that of the host star more closely. Each scenario explains one part of the evidence while leaving another question unanswered. Simply calling GJ 504b a planet or a brown dwarf may therefore create a greater sense of certainty than the current data allows. A name is useful for telling a story, but nature is not always divided into clearly separated categories. The boundary between the largest gas planets and the lightest brown dwarfs may not be a thin line. It may be more like a transition zone where objects with similar masses can have very different formation histories. GJ 504b lies directly within that uncertain region. It forces astronomers to distinguish between what is actually being observed and the story used to explain those observations. What is observed is an infrared point of light moving together with the star GJ 504. It lies at a great separation, has a temperature of several hundred degrees, and emits a measurable amount of light. These details are relatively certain. Its age, mass, and origin are inferred from models. Those estimates may become more precise as better data becomes available, but they should not yet be treated as fixed and unchanging values. The first payoff of this story is therefore not a definitive answer. It is a change in the way the question is asked. GJ 504b is no longer simply a pink planet orbiting far from its host star. It is an object that may be nearly 25 times more massive than Jupiter, large enough to enter the region commonly associated with brown dwarfs, while still carrying clues that prevent a planet-like origin from being ruled out. To move closer to an answer, astronomers need more than an image and more than a measurement of brightness. They need to know which layers of gas the light from GJ 504b has passed through, which molecules have absorbed parts of it, and which clouds have obscured it. They need to separate that tiny point of light into its individual chemical signatures. Most planets beyond the solar system are not discovered by taking pictures of the planets themselves. In most cases, astronomers know a planet exists only because it leaves a very small effect on its host star. Some planets pass in front of their stars from Earth's point of view, causing the starlight to dim for a short period of time. Others do not pass in front, but their gravity pulls the star back and forth by a very small amount. These changes can be far too subtle for the human eye to notice, yet instruments sensitive enough can still measure them. From the slight dimming or motion of the star, researchers infer that an unseen world is orbiting around it. These methods have helped humanity discover thousands of exoplanets, from small rocky worlds to gas giants larger than Jupiter. However, they do not truly allow us to see the planet's own light. They are more like knowing that someone is standing behind a curtain because we can see their shadow or notice that the curtain has moved slightly. The observer may know that something is there and may even estimate its size or motion, but the object itself has still not been seen directly. Directly imaging an exoplanet is a different task. Instead of measuring only the effect the planet has on its star, the telescope attempts to collect light coming from the object itself. That light may be a portion of the star's light reflected by the planet, or heat emitted by the planet from within. It may sound as though the challenge is simply to magnify the image enough But the real difficulty does not lie mainly in size. It lies in the enormous difference in brightness between the star and the planet. A star like the Sun produces an immense amount of light. A nearby planet may be millions or billions of times fainter, depending on its size, temperature, and the wavelength being observed. From a great distance, the two objects also appear very close together in the sky. The planet's faint light can therefore be easily swallowed by the glare of the star. Even if the instrument is sensitive enough to record that small amount of light, it must still distinguish between the planet's true signal and starlight that has simply scattered into the surrounding region. Imagine a glowing ember lying near a powerful searchlight. If the searchlight is switched off, the ember still gives off a faint red glow and can be seen in the darkness. But when the searchlight is turned on, that small glow nearly disappears. If the observer is standing very far away, the two sources may even overlap and appear as a single area of light. The problem facing astronomers is not that the ember produces no light. The problem is that its light is extremely weak beside a source that is vastly brighter. GJ 504b belongs to the rare group of objects with more favorable conditions for direct observation. In images, it lies far enough from its host star to create sufficient separation for researchers to distinguish the faint point from the brightest regions surrounding the star. At the same time, the object is still emitting heat from within. It does not merely reflect light from GJ 504. It also radiates infrared energy as it slowly cools over time. At infrared wavelengths, the difference in brightness between the object and its star becomes less extreme than it is in visible light, although the contrast remains enormous. This is why directly imaged planets and companion objects often do not resemble Earth. They are usually large, still relatively warm, and located far from their host stars. These characteristics do not necessarily represent most of the planets in the galaxy. They are simply the conditions that make such objects easier to detect with current technology. A small, cool planet orbiting close to its star may be very common, yet from a distance, it can disappear almost completely into the star's light. Even with a favorable target such as GJ 504b, finding the point of light required many stages of processing. The Subaru telescope stands near the summit of Mauna Kea, where the air is thinner and drier than it is at lower elevations, creating better conditions for infrared observations. Even so, light from space must still pass through Earth's atmosphere before reaching the telescope's mirror. The air is always moving. Layers with different temperatures and densities bend the light slightly from moment to moment. This is what causes stars to appear to twinkle when viewed with the naked eye. Twinkling may be beautiful when looking at the night sky, but for a telescope trying to find an extremely faint point beside a star, it is a major obstacle. The image of the star constantly shakes and blurs, causing its light to spread into the surrounding region. A companion object that is already faint can be hidden beneath these distortions. Subaru uses a system capable of measuring the way the atmosphere distorts incoming light and then adjusting a mirror many times within a very short period. This process helps make the image of the star sharper and more stable. The system is commonly called adaptive optics. The name may sound complicated, but the basic principle is fairly simple. The atmosphere continuously changes the image, while the mirror changes shape to compensate for those distortions. It does not remove the atmosphere, but it allows the telescope to respond quickly enough to reduce much of the blurring and motion. As a result, the region of light around the star becomes more compact, increasing the chance of detecting a faint object nearby. Making the image sharper, however, is still not enough. The star remains far too bright. Researchers must also reduce some of its direct light. Certain instruments use a component that blocks the central region, much like placing a small object in front of the sun with your hand, while still looking at the surrounding sky. Even then, the starlight does not disappear completely. It still creates spots, rings, and other patterns of interference in the image. These structures can look very much like a small planet, Finding a point of light in a single image is therefore not enough to prove that it is a real world. The point could simply be leftover starlight, an instrumental error, or a much more distant background star that happens to lie along the same line of sight. The next important step is to determine whether the point remains stable and how it moves over time. The star GJ 504 is not motionless in the sky. Like every other star, it moves through space. From Earth, its position changes very slowly relative to the more distant background stars. If the small point of light were merely a star located far behind it, the point would not remain in the same relative position beside GJ 504 over time. As the main star moved, the background object would appear to slide in a different direction across the image. But if the point of light were a true companion, it would move through the sky along with the star system. The distance and direction between the two objects might change slowly because of orbital motion, but they would continue traveling together. Astronomers therefore observed GJ 504 at several different times. They did not take a single image and immediately draw a conclusion. They compared the position of the faint point across multiple observations, checking whether it shared the motion of the host star. The results showed that the small point of light was moving together with GJ 504. It was not left behind like a distant background star. This was important evidence that the object truly belonged to the system. Only after the background star possibility had been ruled out and the signal had been detected repeatedly could researchers regard GJ 504b as a directly imaged companion. Even so, the phrase directly imaged can create an inaccurate impression. It does not mean that Subaru saw a round globe, identified its equator, or observed storms moving through its atmosphere. GJ 504b remained only a tiny point of light, too small in the image to be separated into individual details. What was imaged directly was the light coming from the object itself, rather than only its shadow or its gravitational influence on the star. This distinction is important. A direct image in astronomy does not necessarily resemble a photograph taken with a phone. When we photograph a nearby mountain, each part of the image corresponds to a different region of its surface. With GJ 504b, however, all the light from the object is compressed into a very small number of pixels. Every cloud, every atmospheric layer, and every region of temperature, if they exist, is blended into the same point. Researchers cannot look at that point of light and identify the poles, a cloud layer, or a storm. Instead, they measure the total amount of light and examine how its strength changes across different wavelengths. Even without much spatial detail, that light still contains physical information. A hot object emits energy differently from a cool one. An atmosphere containing methane reduces the light in different regions than an atmosphere containing carbon monoxide. Clouds can prevent light from deeper layers from escaping, changing the object's overall brightness. Direct imaging is therefore not the end of the observing process. It simply creates an opportunity to study the object's own light without depending entirely on the host star. For some planets discovered through transits, astronomers can study the atmosphere when starlight passes through the thin layer of gas surrounding the planet. With GJ 504b, because it appears far from the star in the image, researchers can collect thermal radiation emitted directly by its own atmosphere. Before the James Webb era, however, the amount of light that could be collected was still limited. Subaru and other ground-based telescopes could record the object in several infrared regions, measure its relative colors, and estimate its temperature. Those observations led to the discovery of GJ 504b and showed that it differed from many previously known companion objects. But its atmosphere still did not appear clearly enough in the data. Part of the difficulty came from Earth's atmosphere. The air does more than make an image shake and blur. It also absorbs many regions of infrared light. Water vapor, carbon dioxide, and other molecules in our planet's atmosphere leave their own signatures on light arriving from space. Some wavelengths are almost impossible to observe effectively from the ground because they are blocked before reaching the telescope. Researchers had to separate the signal from GJ 504b from the star's light, instrumental noise, and the imprint of Earth's atmosphere. It was like trying to hear a quiet voice on the other side of a room, while a loud speaker was playing nearby, and a sheet of glass between the two people was distorting the sound. Subaru helped confirm that the quiet voice truly existed. It measured part of the signal's strength and character. But hearing each word clearly required a quieter environment and a more sensitive instrument. Its location in space gives James Webb an important advantage. The telescope does not have to look through Earth's atmosphere, allowing it to observe more clearly many infrared wavelengths that air absorbs. Its cold and stable operating environment also reduces the heat emitted by the instrument itself, which is especially important when the target is an extremely faint infrared source. But James Webb did not return to GJ 504b merely to produce an image with higher resolution. Even through this telescope, the object does not become a globe with clearly visible cloud bands. Its greatest value lies in the ability to collect more light and separate it into a detailed spectrum. The roles of Subaru and James Webb can be understood as two consecutive steps. Subaru found the small point of light, demonstrated that it moved together with the star, and confirmed that it was a companion object. James Webb then asked a deeper question: what kind of light forms that point, and what traces have its atmospheric layers left within it? This is also how many astronomical discoveries develop. One instrument detects something unusual. Later observations confirm that it is real. A new generation of telescopes then examines details that the earlier instrument could not reach. No single telescope answers every question. Each tool opens a new layer of information. For GJ 504b, the first layer was the existence of the point of light. The next was its temperature and infrared color. Then came questions about its age, mass, and true nature. But to determine what the atmosphere contained, imaging measurements alone were no longer enough. Finding GJ 504b was like noticing that a light was shining behind a very distant window. We know that a source of light is there. We can measure how bright it is and how it changes over time. But to understand what lies inside the room, we must study the light more carefully, examining which colors remain and which were absorbed before the light escaped. Finding the point of light only confirmed that the object existed. To discover what was hidden inside that light, astronomers needed to transform the point into a spectrum of wavelengths. In the first images of GJ 504b, the entire object was contained within a tiny point of light. Ground-based telescopes could measure how bright or faint that point appeared in a few infrared regions, allowing researchers to estimate its temperature and compare it with known gas giants and brown dwarfs. But those separate measurements were like seeing only a few colors taken from a much larger painting. They could suggest whether the picture was bright or dark, warm or cool, but they were not enough to reveal the subtle details hidden within it. To determine which molecules were present in the atmosphere of GJ 504b, which cloud layers were blocking its light, and how material was moving between different atmospheric levels, astronomers needed an almost continuous band of light rather than only a few isolated measurements. That was something ground-based observations had not been able to accomplish fully for this object. GJ 504b was already extremely faint, while the nearby host star was vastly brighter. Light from the system also had to pass through Earth's atmosphere, where water vapor, carbon dioxide, and many other molecules absorb infrared radiation. The signatures belonging to our own planet could overlap with the signal from the distant world. The moving atmosphere also caused the image of the star to change continuously, spreading its light into the surrounding region and mixing it with the position of the companion object. Ground-based telescopes were powerful enough to confirm that GJ 504b existed and to measure its brightness through several filters, but the point of light remained too faint to produce a complete spectrum with the level of detail researchers needed. James Webb changed the situation not by magnifying GJ 504b into a sharply defined globe, but by collecting and analyzing faint infrared light with far greater sensitivity. The telescope operates beyond Earth's atmosphere in a cold and relatively stable environment. Light from GJ 504b no longer has to pass through the water-rich air of our planet before reaching the instrument. The telescope itself is also shielded from most of the heat coming from the Sun and Earth, reducing the infrared background that could overwhelm the signal from such a faint object. These advantages do not remove every difficulty, but they create a much cleaner observing environment than the one available from the ground. The instrument used for this work was NIRSpec, the near-infrared spectrograph aboard James Webb. Its task is not simply to take a picture. NIRSpec receives incoming light and separates it into many smaller wavelength regions. The principle is somewhat similar to the way a prism spreads white light into a band of colors, although most of the region observed by NIRSpec lies beyond the range of human vision. Instead of red, orange, yellow, or blue, the instrument records near-infrared regions identified by their wavelengths. Each region carries a different part of the story about the atmosphere's temperature and composition. For GJ 504b, the process can be understood as 3 consecutive tasks. First, James Webb had to collect the very small amount of light coming from the object's position. The research team then had to remove light that did not truly belong to it, especially the glow from the host star, background signals, and structures created by the telescope's optical system. Only after that could the remaining light be spread into a spectrum showing how much energy the object emitted at each wavelength. These 3 steps may sound simple, but the most difficult part often lies in the second one. GJ 504b was present in the data from the beginning, but to reveal its true signal, researchers had to peel away several layers of brighter light covering it. Even in space, a star does not appear as a perfect point with sharply defined edges. As its light passes through the telescope's mirrors and optical components, it forms a characteristic pattern consisting of a bright central region surrounded by fainter structures. This pattern is commonly called the point spread function. It is not an unusual error, but a natural result of the way light travels through an optical system of limited size. The problem is that GJ 504b lies within the region affected by this pattern. Some of the signal at the object's position actually comes from the star, and this leaked starlight may be stronger than the companion itself. The research team therefore had to construct an accurate description of how the star's light appeared in the data. They tracked its shape at different positions and wavelengths, then estimated how much of it would extend into the region occupied by GJ 504b. Once the model of the starlight was subtracted, the weaker signal from the companion began to emerge. This process was not like removing a star from an image with one simple command. If too little was subtracted, leftover starlight would distort the spectrum. If too much was removed, part of the real signal from GJ 504b could disappear as well. The researchers therefore had to test the method in several ways, making sure that the features appearing after processing were not artifacts created by the processing itself. In addition to the starlight, the data contained a weak infrared background from several other sources. Dust within the solar system, distant regions of space behind the target, residual heat inside the instrument, and small differences between parts of the detector could all contribute to this background. For a bright object, these effects might represent only a very small fraction of the signal. For GJ 504b, they became significant because the light being measured was already so faint. The team had to determine the background level, calibrate the sensitivity of the detector, and track how the image changed with wavelength before they could trust the final spectral curve. After these stages of processing, GJ 504b was no longer simply a point with one overall brightness. Its light had been spread across wavelengths ranging approximately from 2.9 to 5.3 micrometers. A micrometer is an extremely small unit equal to 1/millionth of a meter. The light visible to human eyes occupies a shorter part of the wavelength scale, while the region used to study GJ 504b lies deeper in the infrared. This is where an object with a temperature of several hundred degrees emits a significant amount of energy, and where many atmospheric molecules leave clear signatures. There is no need to remember the numbers 2.9 and 5.3 micrometers. What matters is that the new spectrum did not consist of only a few separate measurements. It covered a broad and detailed enough range for molecular features to begin separating from one another. Previously, if a filter measured the total light within a broad region, several different signatures could be blended into a single number. With NearSpec, that region was divided into much smaller sections. Places where the light rose, fell, or changed slope began to appear as distinct structures. The final result does not resemble an image of a planet. It is a line extending horizontally across a graph. Each position along the horizontal axis corresponds to a wavelength, while the height of the line shows how much light GJ 504b emits at that wavelength. In some regions, the spectrum rises because more energy escapes. In others, it falls because part of the light has been absorbed by molecules in the atmosphere or blocked by clouds before it could leave the object. Viewed on its own, this rising and falling line may not seem as impressive as an image of a pink planet. It has no horizon, no cloud bands, and no easily recognizable regions of light and darkness. Scientifically, however, it contains far more information than an imagined close-up illustration. An artwork may suggest what GJ 504b could look like if observed from nearby, but the spectrum allows researchers to test how the real atmosphere is interacting with light. Importantly, the spectral line is not drawn according to what the researchers want to see. It is produced from the number of photons recorded by the detector at each wavelength after the data has been calibrated. Atmospheric models are introduced only afterward, when the team begins trying to explain the shape of that line. The data comes first, the explanation comes later. If a model predicts that the light should be strong in one region, but the observations show that it falls instead, the model must be adjusted. Scientists cannot alter the spectrum to make it fit a pre-existing idea. Even so, a spectrum is not a simple copy of the atmosphere. The observed light may emerge from many different depths. At one wavelength, the atmosphere may be relatively transparent, allowing radiation from deeper and hotter layers to escape. At another, a molecule may absorb strongly, so the telescope receives light only from higher and cooler regions. Clouds may block even more of the radiation coming from below. Each part of the spectrum is therefore like a window looking into a different atmospheric depth. But those windows overlap, and their boundaries are never completely clear. James Webb does not create a weather map of GJ 504b either. All the atmospheric regions facing the telescope are blended together within the collected signal. If one half of the object is cloudier than the other, the original spectrum mainly shows the combined result of both sides. If storms or atmospheric bands exist, they remain too small to be resolved as individual structures. What is new is that, for the first time, scientists can directly analyze the object's light in enough detail to search for distinct chemical signatures. GJ 504b can be imagined as a person standing very far away in the darkness. Ground-based telescopes confirmed that the person was there and measured the faint light coming from that location. James Webb did not bring the person closer, but it separated the signal into many parts, as though we were hearing a voice for the first time, instead of merely knowing that a faint sound existed in the distance. This voice is not made of words or sound. It is formed by the regions of light that remain and the regions that were absorbed within the atmosphere. Every molecule interacts with light in its own way. Water vapor does not absorb infrared radiation in exactly the same way as methane. Carbon monoxide leaves a different signature from carbon dioxide. Ammonia affects another region. These signatures, however, do not stand apart like simple lines that can be read immediately. They extend across broad regions, overlap one another, and change with temperature, pressure, and atmospheric depth. That is why the team needed a detailed spectrum not to find one isolated sign, but to determine which combination of molecules could explain the complete shape. Obtaining the spectrum also made it possible to measure characteristics that could not be determined confidently from an image alone. The overall slope of the light is related to temperature. The depth of the absorption regions reflects the amount of each molecule and the atmospheric level from which the light can escape. The shapes of certain features are also influenced by pressure and gravity. If the atmosphere is strongly mixed between its deeper and higher layers, the proportions of molecules may differ from their stable equilibrium values. If clouds are present, parts of the spectrum that would normally come from deeper layers will appear weaker. Before drawing those conclusions, however, the researchers had to answer a more basic question: which molecules truly produce the dips in the spectrum? This is not a matter of looking at one low point and immediately attaching the name of a gas to it. A single region may be affected by several molecules at once. Temperature and clouds can also change the overall shape. Scientists therefore had to compare the observed spectrum with many different atmospheric models, changing the composition, temperature, gravity, and cloud thickness one by one to determine which combination reproduced the full set of data most successfully. From this point, the tiny point of light began to reveal a story of its own. It was not a story created from pink cloud bands in an illustration, but one recorded within every portion of light that passed through the atmosphere and then traveled for nearly 60 years before reaching James Webb. Some of the light escaped almost unchanged. Some was weakened. Some never left the deeper atmospheric layers at all. The spectrum contained many downward dips. Each dip represented a portion of missing light, and those missing portions began to reveal the atmosphere. The dips in the spectrum of GJ 504b do not appear at random. They form because light interacted with molecules in the atmosphere before escaping into space. Some wavelengths passed through relatively easily, while others were absorbed more strongly. When James Webb measured the light that remained, the weakened regions appeared as depressions in the spectral curve. Each type of molecule interacts with light in a different way. Water vapor does not absorb the same wavelengths as methane, while carbon monoxide creates a different pattern from carbon dioxide. The reason lies in the structure of each molecule. When molecules receive energy from light, they can vibrate or rotate in specific ways. They absorb most strongly only the parts of the light that match those motions. Because every molecule has a different structure, each one produces a different absorption pattern. Imagine light from the deeper layers of GJ 504b trying to pass through several layers of gas before escaping. Each layer removes a different portion. By the time the light finally reaches James Webb, it no longer has its original shape. The missing parts become clues to what it encountered along the way. A molecule, however, does not produce only one isolated line that is completely separate from everything else. Under real atmospheric conditions, a substance usually affects an entire range of wavelengths. Temperature and pressure can broaden those features, change their depth, or blend them with the signatures of other molecules. The spectrum is therefore not like a simple codebook, in which every dip immediately corresponds to the name of one chemical. It is more like a piece of music in which several instruments are playing at the same time. Hearing a single note may not reveal whether it came from a stringed instrument, a flute, or something else. But by listening to the entire sequence, the rhythm, and the way the tone changes, a listener can begin to identify the different parts of the arrangement. Astronomers do something similar with a spectrum. They do not look at one dip and immediately declare that they have found a molecule. They examine the complete shape of the band of light and search for a pattern that matches across several regions at once. These patterns are not created through free speculation. In laboratories, scientists have measured how many molecules absorb light at different temperatures and pressures. Physical calculations also make it possible to predict the locations and strengths of absorption regions. From this work, researchers build databases describing the signature of each substance. When a spectrum from a distant world is obtained, the observed pattern can be compared with those results. Even so, the comparison is not a simple process of matching individual lines. The atmosphere of GJ 504b contains several substances at the same time. The signature of water vapor may overlap with that of methane. Carbon monoxide may affect a region close to one where carbon dioxide also absorbs. Clouds can reduce the amount of light escaping from deeper layers, making some features appear weaker than they would in a completely transparent atmosphere. The research team, therefore, had to test many different models rather than searching for each molecule separately. Each model describes a hypothetical atmosphere with a particular temperature, pressure, and composition. From those conditions, a computer calculates the spectrum that such an atmosphere would produce. The simulated curve is then placed beside the James Webb data. If a model containing methane but no water vapor explains only a small section of the spectrum, it cannot yet be considered a good match. If adding another molecule improves one region but causes several others to move farther from the data, the model still needs to be adjusted. The researchers are looking for a combination that can explain most of the spectral shape at the same time. Evidence for a molecule is considered reliable only when its signature appears consistently in the regions predicted by physics, and when including it improves the agreement between the entire model and the data. This approach reduces the risk of mistaking a random fluctuation or an overlapping feature for genuine chemical evidence. 24. It is also important to distinguish clearly between the observations and their interpretation. James Webb directly records the amount of light at each wavelength. That is the observational part. Determining how much water, vapor, methane, or another substance is present comes from comparing the spectrum with atmospheric models. The data does not display the name of each molecule on its own. Those names appear only after many alternative possibilities have been tested. Scientists have not collected a sample of air from GJ 504b either. No gas tube has been sent to that world, and not a single particle from its atmosphere has been returned to a laboratory. All the information comes from light. The result is therefore not like a chemical test performed directly at the location. It is a remote inference, but one constrained by physical laws that have been measured and tested. A distance of nearly 60 light-years does not prevent light from carrying information. Every photon that reaches the telescope has completed a long journey, but before leaving GJ 504b, it passed through layers of gas with different temperatures and compositions. Some photons escaped, some were absorbed and later re-emitted in another direction. Others never reached the observer at all. The spectrum is the surviving record of that process. The depth of an absorption region does not automatically reveal the exact number of molecules present. A strong feature may result from a large amount of a substance, but it may also be affected by temperature, pressure, or the altitude where the light originated. If clouds block the deeper layers, the entire underlying spectrum changes. Chemical composition, temperature, and clouds must therefore be considered together. This is why analyzing an atmosphere requires many models rather than a single direct reading. Despite these limitations, the spectrum of GJ 504b is far clearer than the observations available before James Webb. The wavelength range collected by the telescope contains enough detail that many absorption regions no longer blend into one vague signal. The patterns begin to separate, allowing the team to test several molecules at the same time and reject explanations that are too simple. From a tiny point of light, GJ 504b now emerges as an atmosphere with a complex chemical structure. Humanity still cannot see those layers of gas directly, but we can recognize the marks they leave in the light. Like identifying several instruments by listening to an entire passage of music rather than a single note, astronomers combine the absorption regions to find the most reasonable arrangement. And when those fingerprints are assembled, the atmosphere of GJ 504b reveals more components than early predictions suggested. When the spectrum of GJ504b was compared with atmospheric models, several chemical signatures began to emerge at the same time. Within the object's faint light, the research team identified evidence of water vapor, methane, carbon monoxide, carbon dioxide, ammonia, and hydrogen sulfide. The spectrum was detailed enough to reveal several forms of carbon monoxide as well, containing carbon or oxygen atoms with slightly different masses. The important point, however, is not simply to compile a list of the substances that were found. The more interesting question is why they appear together in a relatively cool atmosphere, in proportions that a simple model cannot easily explain. The signature of water vapor is one of the most immediately striking features. In everyday life, water is often associated with oceans, rain, and life. But detecting water vapor on GJ504b does not mean that this object has seas, rivers, or a habitable surface. GJ504b is a giant gaseous world, with an inferred atmospheric temperature far above the boiling point of water under familiar conditions on Earth. The spectrum tells us only that water molecules exist as a gas within the atmospheric layers from which light can escape. It does not reveal an ocean below, nor does it provide any evidence of living organisms. Water is not a rare molecule in the universe. Hydrogen and oxygen are both abundant, so water molecules can appear within gas clouds, disks surrounding young stars, planetary atmospheres, and many environments unrelated to life. On a gaseous world such as GJ504b, water vapor is primarily a clue that helps researchers determine the atmosphere's temperature, composition, and the depths being sampled by the spectrum. At some wavelengths, water vapor absorbs strongly, preventing light from deeper layers from escaping. In other regions, the atmosphere is more transparent, allowing us to see slightly farther down. The water signature, therefore, does more than confirm the molecule's presence. It also helps reconstruct the atmosphere's thermal structure. Methane is another prominent component. This molecule is made of carbon and hydrogen and often appears clearly in the atmospheres of relatively cool giant worlds. Within the solar system, methane is present in the atmospheres of Jupiter, Saturn, Uranus, and Neptune, although in different amounts. It is not a signature unique to biological activity. Under suitable conditions of temperature, pressure, and chemical composition, methane can form entirely through processes that have nothing to do with living organisms. In very hot objects, carbon is more likely to exist in the form of carbon monoxide. As the temperature falls, methane can become more favorable. Because GJ504b is much cooler than many young planets that have been directly imaged, a strong methane signature in its spectrum is something researchers might expect. The problem begins when methane is considered alongside carbon monoxide. If the atmosphere were in complete equilibrium, the temperature of each layer would determine which form of carbon should dominate. Chemical reactions would gradually move the material toward the proportions most stable under the local conditions. But the spectrum suggests that methane and carbon monoxide coexist in a way that indicates the atmosphere may not remain still long enough to reach that state. Carbon monoxide consists of one carbon atom bonded to one oxygen atom, while carbon dioxide contains an additional oxygen atom. These two molecules help researchers trace how carbon and oxygen are distributed throughout the atmosphere. They also respond differently to temperature and pressure, so the ratio between them carries information about the atmospheric layers through which the material has traveled. If carbon monoxide forms in a deeper and hotter region and is then carried upward, it may remain there for some time before it can transform into a form more suitable for the cooler air above. Its presence therefore reveals more than composition. It also suggests that material is moving between different depths. Carbon dioxide appears in smaller amounts, but it remains valuable. Its signature provides another way to examine how carbon and oxygen participate in different reactions. In a less detailed spectrum, this feature could easily blend with the signatures of other molecules. The fact that James Webb can distinguish it demonstrates how much farther the new data has advanced beyond the separate infrared measurements available before. Even so, the team still has to consider the full spectrum, because the strength of the carbon dioxide signature depends not only on the number of molecules, but also on temperature, pressure, and the influence of clouds. Ammonia adds another layer of information. This molecule consists of nitrogen and hydrogen, and often appears in the atmospheres of relatively cool giant worlds. Like methane, the observed amount of ammonia can change if the atmosphere is undergoing strong mixing. In deeper and hotter regions, nitrogen may exist in another form. When gas is carried upward into cooler layers, the chemical reactions need time to rearrange the composition. If the movement occurs quickly enough, the atmosphere may preserve an ammonia abundance that differs from what the temperature of the observed layer would normally predict. Ammonia is therefore more than another name added to the list. It helps test whether the evidence for mixing inferred from carbon monoxide and methane is consistent. When several groups of molecules point in the same direction, the case for strong atmospheric movement between different layers becomes more convincing. A single signature may be affected by noise or overlap, but several features supporting the same picture provide stronger evidence. Hydrogen sulfide was also identified in the spectrum. This molecule contains sulfur and can exist within hydrogen-rich atmospheres. On Earth, it is commonly associated with the smell of rotten eggs, but that comparison has little relevance to a distant object. What matters is that the hydrogen sulfide signature allows the research team to trace another element in addition to carbon, oxygen, and nitrogen. The abundance of sulfur may help compare the composition of GJ504b with that of its host star and test different formation scenarios. The spectrum also reveals several isotopic forms of carbon monoxide. Isotopes are versions of the same element whose atomic nuclei contain slightly different numbers of particles. They still participate in similar molecules, but their small differences in mass shift the way they absorb light by a subtle amount. There is no need to examine each isotope in detail to understand the importance of this finding. The fact that such delicate features can now be recognized already demonstrates the level of detail in the new data. The point of light that once had only one overall infrared color has now been separated finely enough for small variations within the same molecule to be examined. Even so, finding more molecules does not mean that every question has been resolved. On the contrary, when these molecules are considered together, the atmosphere becomes more difficult to understand. If only methane and water vapor were present, a relatively cool atmospheric model might reproduce much of the spectrum. But once carbon monoxide, carbon dioxide, and ammonia are included, the proportions between them begin to suggest an atmosphere that is not completely still. Within a layer of gas left undisturbed for long enough, chemical reactions gradually adjust the composition to match the local temperature and pressure. Molecules that are unstable under those conditions become less abundant, while more stable forms increase. But the atmosphere of a giant world is not an unmoving layer of gas. Heat continues to escape from the interior. Warmer gas can rise while cooler gas moves downward. Material is transported between regions with very different conditions. As a result, the spectrum reflects not only the place where the light finally escapes, but also carries traces of deeper atmospheric layers. A molecule formed in a hot region may be transported upward before it has time to transform. A substance favored in the upper atmosphere may be drawn downward and enter different reactions. The observed composition is therefore shaped by both chemistry and movement. This is what makes GJ504b especially interesting. The researchers are not merely detecting water, vapor, methane, or carbon monoxide as isolated substances. They are seeing a combination in which several molecules appear not to have had enough time to rearrange themselves into a stable state. Their proportions resemble a photograph taken while the process of change is still unfolding, rather than after everything has completely settled. Atmospheric mixing, however, is not the only factor affecting the spectrum. Clouds can block some of the light from deeper layers, making certain molecules appear less abundant than they truly are. Temperature also changes the strength of the absorption regions. The researchers therefore cannot simply adjust the amount of each substance until the model curve matches the data. They must find an atmosphere in which the composition, temperature, movement, and clouds are all physically reasonable together. The detection of several molecules is therefore only the beginning. It shows that GJ504b possesses an atmosphere far richer than the first few infrared measurements could reveal. But that richness also creates a new problem. When all the substances are placed within the same model, some of their proportions do not match an atmosphere that is quiet and has reached chemical equilibrium. The atmosphere appears to be carrying material upward from deeper layers faster than the molecules can rearrange themselves. The molecules detected in the atmosphere of GJ504b reveal more than the elements contained within the object. When considered together, the proportions of methane, carbon monoxide, ammonia, and other substances also show that the atmospheric layers are not completely still. The composition recorded by James Webb appears not to have had enough time to adjust to the temperature of the region where it currently exists. This is a sign of an atmosphere that is not in chemical equilibrium. The idea can be understood quite simply. If a quantity of gas remains at the same temperature and pressure for long enough, the reactions within it will gradually bring its composition toward a relatively stable state. Molecules that are more favorable under those conditions become more abundant, while less stable forms gradually decrease. The system does not necessarily stop changing entirely, but the forward and reverse reactions eventually reach a point where the overall proportions no longer change significantly. In a laboratory, scientists can create nearly stable conditions and then wait to see how a mixture of gases changes. But the atmosphere of a giant world is not a container being held still. Beneath the layers that telescopes can probe lies a deeper body of gas that is hotter and under far greater pressure. Heat continues moving outward from the interior. Material, at different depths, continually exchanges positions, allowing molecules formed under one set of conditions to be carried quickly into another. A simple comparison would be a pot of liquid being stirred. Material near the bottom is carried upward before it has time to separate or transform completely, while material at the surface moves downward. The atmosphere of GJ504b is not literally like a pot of water, but the comparison helps clarify one point. When transport occurs faster than chemical reactions, the composition of each layer no longer depends only on the conditions within that layer itself. Carbon monoxide is an important example. This molecule is generally favored in hotter regions. In cooler layers, carbon tends to move into other forms, including methane. If a parcel of hot gas rises slowly from below, the carbon monoxide has enough time to take part in reactions and gradually decrease. But if the material is carried upward quickly enough, some carbon monoxide may survive at altitudes where ordinary equilibrium models predict that much less of it should remain. Methane tells the other part of the story. GJ504b is relatively cool compared with many directly imaged companion objects, so a strong methane signature is reasonable. But methane does not exist independently of carbon monoxide. Both contain carbon and are connected through a network of chemical reactions. The ratio between them depends on temperature, pressure, and the amount of material transported from one atmospheric layer to another. When the observed ratio does not match the stable condition expected within the layer emitting the light, it suggests that the composition carries a memory of somewhere else. Ammonia provides a similar test for nitrogen. At different depths and temperatures, nitrogen may be favored in different molecular forms. If the atmosphere remains still for long enough, the amount of ammonia in a particular layer will move toward the level allowed by the local temperature and pressure. But if material is continually transported vertically, the observed ammonia abundance may be lower or higher than predicted. When both carbon-bearing and nitrogen-bearing molecules point toward the same possibility, the evidence for atmospheric mixing becomes stronger. This does not mean that James Webb directly observed masses of gas rising and falling. The telescope does not record separate columns of air, nor has it measured the exact shape of the atmospheric circulation. There is no map showing which regions are rising and which are sinking, and the current data does not allow researchers to describe the wind speeds precisely. The conclusion about mixing is inferred from the chemistry. The molecules appear in proportions that would be difficult to maintain if every atmospheric layer had remained still long enough to reach equilibrium. Disequilibrium chemistry, therefore, does not mean that the atmosphere is behaving chaotically in some unnatural way, nor does it mean that the laws of chemistry are being broken. On the contrary, familiar chemical laws are exactly what allow researchers to recognize what is happening. They know which proportions a gas mixture at a particular temperature and pressure should tend toward. When the spectrum reveals a different ratio, they look for a physical process that could continually interrupt that adjustment. For GJ 504b, the transport of material between hotter, deeper layers and cooler upper regions provides a suitable explanation. The observed composition therefore reflects more than present conditions. It also contains traces of the journey taken by the gas. A molecule found in the upper atmosphere may have formed much deeper below. Before it had time to transform completely, it was carried into a region where light could escape into space. The spectrum records the molecule at that final location, but its abundance still carries information about the places it passed through. It is similar to seeing a warm object that has just been moved from a heated room into a cold one. If an observer measured only the temperature of the current room, the object might be expected to be cooler, but the heat it still retains shows that it arrived recently and has not had enough time to adjust. In the atmosphere of GJ 504b, the molecules act somewhat like these lingering traces. They show that the material left a region with different conditions before the chemistry could fully rearrange itself. Atmospheric models test this process by changing the strength of vertical mixing. If material is assumed to move too slowly, some molecules in the simulated spectrum appear weaker or stronger than they do in the real data. When the amount of mixing is increased, the proportions of methane, carbon monoxide, and ammonia move closer to the observations. No single molecule forced the research team toward this conclusion. The reliable evidence came from the fact that several regions of the spectrum improved at the same time. The new study therefore indicates that GJ 504b shows clear chemical disequilibrium. This is an important result because it transforms the spectrum from a list of ingredients into evidence of movement. James Webb does not merely reveal that the atmosphere contains methane or carbon monoxide. The data also shows that these substances are being distributed through a deep atmosphere, where heat from the interior continues to drive the exchange of material between layers. Mixing also affects how mass and temperature are inferred. If a model assumes that the atmosphere has reached complete equilibrium, it may need to alter molecular abundances or temperature in order to explain the spectrum. But once vertical motion is included, part of the chemical difference can be explained without making unreasonable adjustments. This brings the model closer to an atmosphere that could physically exist, rather than one that merely produces a similarly shaped spectral curve. Chemical disequilibrium, however, does not explain every detail. Even after the team allowed material to move between atmospheric layers, some regions of the spectrum still failed to match. At certain wavelengths, the model predicted that too much light should escape from below. Some molecular signatures also appeared stronger in the model than James Webb had observed. If the researchers changed only the composition or the amount of mixing, improving one region often caused another to fit less successfully. This suggests that molecules are not the only things absorbing or blocking the light. Another component is obscuring some of the radiation from deeper and hotter atmospheric layers before it can escape. This component does not leave a clear fingerprint like methane or water vapor, but it changes the underlying shape of the entire spectrum. Vertical mixing explains part of the spectrum, yet some of the light is still being dimmed in a way that individual molecules cannot explain. After accounting for mixing between atmospheric layers, The models of GJ504b were better able to explain the proportions of methane, carbon monoxide, and ammonia. Molecules favored in deeper regions could be carried upward before they had time to transform completely, causing the observed composition to depart from chemical equilibrium. Yet when the simulated spectrum was placed beside the James Webb data, several differences remained. The problem did not involve only one isolated chemical signature. Both the object's overall brightness and the relative depths of many absorption regions still failed to match. This is where atmospheric modeling becomes especially important. A model is not an image drawn from imagination. It is a system of calculations based on known physical laws. The research team selects a temperature, a level of gravity, a mixture of molecules, and a description of how material moves through the atmosphere. From those conditions, a computer calculates how much light should escape at each wavelength. The result is a hypothetical spectrum, which is then compared with the spectrum James Webb actually recorded. When the two curves do not match, the researchers cannot simply focus on one point and adjust a number until that point fits. They must examine the entire wavelength range. An adjustment that improves the methane region may make the water vapor signature too strong. Increasing the temperature may improve the brightness in one section while moving the carbon monoxide feature farther from the observations. Changing gravity also affects the pressure, the depths of the absorption regions, and the amount of light emerging from different atmospheric layers. Every assumption produces several connected changes at once. This process is usually repeated many times. Models with different temperatures are tested. Gravity is varied within a reasonable range. Elemental abundances and the strength of vertical mixing are adjusted as well. Each time, the simulated spectrum is compared with the observations to determine not only where it fits, but also where it fails. Regions that remain inconsistent across many models are signs that an important physical component may be missing. For GJ504b, cloud-free models could reproduce several molecular features reasonably well. Methane appeared at approximately the correct wavelengths. Water vapor and carbon monoxide also created absorption regions similar to those in the data. But the total amount of light escaping at certain wavelengths remained too high. Some dips in the models were deeper than those seen by James Webb, while other sections rose above the observed level. The simulated atmosphere appeared too transparent, allowing the observer to see more deeply into the hot layers below than the real data permitted. If only one absorption line failed to match, the cause might simply be an incorrect estimate of one molecule's abundance. But in this case, the differences extended across broad portions of the spectrum. That suggested the problem did not lie entirely with one particular gas. Something was affecting the light before the molecular signatures were recorded, changing both the underlying brightness and the prominence of several absorption features at once. The component most capable of producing such a broad effect was clouds. On Earth, clouds are usually imagined as white or gray masses suspended in the atmosphere. In spectral analysis, however, what matters is not the visible shape of a cloud, but how the small particles within it interact with light. They can absorb, scatter, or block radiation rising from deeper atmospheric layers. A cloud layer does not have to be completely dense to produce a noticeable effect. Simply making the atmosphere less transparent can significantly reduce the amount of light escaping from below. The deeper layers of GJ504b's atmosphere are hotter. If nothing blocks them, radiation from those regions can rise and escape at wavelengths where the gas above is relatively transparent. Those regions would appear brighter in the spectrum. But if a cloud layer lies in the path, it blocks part of the light coming from below. James Webb then receives more of its signal from higher and cooler layers, causing the observed brightness to fall below the level predicted by a cloud-free model. Clouds also change the depths of molecular features. Suppose a large amount of methane exists in the lower atmosphere. If light from that region is partly blocked by clouds, the methane signature may appear weaker even though the molecule is still present in substantial quantities. The same can happen with water vapor, carbon monoxide, and other substances. The spectrum therefore depends not only on what the atmosphere contains, but also on which parts of the atmosphere can actually be seen. Imagine looking into a room through a window. When the glass is completely clear, someone standing outside can see objects deep inside. If a thin curtain is drawn across the window, those objects do not disappear, but their light becomes weaker and their details harder to recognize. The spectrum of GJ 504b is affected in a similar way. Molecules beneath the clouds still exist, but their signals cannot escape with the same strength. This makes clouds an essential part of the model rather than a decorative detail added at the end. In an illustration, clouds may be included to make a planet look more vivid. In a scientific model, clouds determine how deeply the telescope can probe. They alter the apparent temperature, the overall brightness, and the relative strengths of the absorption regions. Ignoring them can cause researchers to misjudge molecular abundances or adjust the temperature in an unrealistic direction simply to compensate for missing light. Adding just any cloud layer, however, is not enough. Different types of particles do not interact with light in the same way. Particle size, cloud altitude, density, and chemical composition all affect the spectrum. A layer made of very small particles may change the light differently from one containing larger particles. High clouds obscure more of the atmosphere than deeper clouds. The composition of the particles also determines which wavelength regions they absorb most strongly. The research team therefore had to test several different cloud models. Each possibility was placed within an atmosphere with an appropriate temperature and composition, and the spectrum was calculated again. If one type of cloud reduced the overall brightness but erased molecular features that James Webb still detected, it was not a good explanation. If the clouds were placed too high, the spectrum could become almost flat. If they were too deep, their influence would be too weak to correct the mismatched regions. This was not a process of random guessing. The temperature of each atmospheric layer determines which substances can remain in gaseous form and which can condense into particles. A compound can form clouds only when the local temperature and pressure allow it to change from vapor into a condensed state. Every cloud type introduced into the model, therefore, had to be consistent with the structure of the atmosphere, rather than being selected merely because it made the spectral curve look better. After every change, the entire band of light was examined again. A successful model could not match only one prominent dip. It had to reproduce the underlying brightness, the overall slope of the spectrum, and the relative depths of several features at the same time. If a cloud layer improved the methane region but caused the carbon dioxide feature to move farther from the data, the model was still inadequate. Only possibilities that improved several portions of the spectrum simultaneously were retained for further consideration. Step by step, a clearer picture began to form. Vertical mixing explained why some molecules appeared in proportions different from chemical equilibrium. Temperature and gravity helped define the atmosphere's general structure. But for the brightness level and absorption features to agree at the same time, a layer of particles was needed to dim the light rising from below. Without that layer, the models consistently looked too deeply into the hotter regions and produced more radiation than James Webb had recorded. What is especially notable is that clouds do not leave an easily readable signature like a gas molecule. Water vapor and methane absorb strongly in relatively characteristic wavelength regions. Clouds usually exert a broader influence, changing the underlying spectrum and the visibility of many features at once. Their presence is recognized not through one isolated line, but through the way the entire spectrum becomes more physically consistent when the cloud layer is included. This is also why the earlier models cannot be described as complete failures. They successfully identified several molecules, narrowed the possible temperature range, and revealed mixing within the atmosphere. The portions they explained helped the researchers recognize where the missing physics was likely to be found. Each mismatch did not invalidate the entire model. It indicated which assumption needed to be examined more closely. Science often moves forward in this way. A model is built from what is already known. New data shows that it is correct in some respects but incomplete in others. Rather than discarding every result, researchers search for a physical factor that could explain the remaining differences, add that factor, and test the model again from the beginning. If the new model corrects one region but disrupts several others, it is rejected. If it improves the full spectrum while remaining physically plausible, the explanation becomes more credible. For GJ504b, the missing component was not a new molecule hidden inside one small spectral dip. It was a layer of material capable of obscuring light from several atmospheric depths at once. When the appropriate cloud layer was added, the simulated spectrum began to dim in the places where it needed to, while the signatures of water vapor, methane, and carbon monoxide remained visible at depths closer to those in the real data. Among the cloud types that were tested, one produced the most suitable change. It was not made of water, but of compounds commonly grouped under the name salts. Once salt clouds were included in the model, the spectrum of GJ504b began to make more sense. Too much light was no longer escaping from the deeper layers, and the signatures of methane, water vapor, and carbon monoxide moved closer to the James Webb data. But the value of the cloud layer extended beyond explaining a few missing regions of light. It also changed how researchers inferred the temperature, gravity, and ultimately the mass of the entire object. James Webb did not weigh GJ504b directly. No instrument placed the object on a gigantic scale, and no spacecraft has flown around it to measure its gravitational pull precisely. Its mass had to be inferred indirectly from its light, by finding an atmospheric model capable of producing a spectrum as close as possible to what the telescope observed. The shape of the spectrum depends on many factors at the same time. Temperature determines how much energy the object emits and which molecules can exist in each atmospheric layer. Gravity affects how tightly the atmosphere is compressed, changing the pressure and the widths of absorption regions. Chemical composition determines which wavelengths are absorbed. Vertical mixing allows certain molecules to appear in places where they have not yet had time to reach equilibrium. Meanwhile, the altitude, density, and properties of the clouds determine how deeply the telescope can see. None of these factors can be considered in isolation. A spectrum that appears consistent with a lower temperature may actually be the result of a thick cloud layer hiding hotter regions below. A molecular signature that looks weak does not necessarily mean that the molecule is rare. It may simply mean that light from the region containing it is being blocked by clouds. If clouds are ignored, the model may compensate by changing the temperature or composition in the wrong direction. The inferred gravity and mass would then shift as well. The research team therefore did not choose a mass in advance and then try to force the spectrum to match it. They tested many different combinations. In each one, the temperature, gravity, molecular abundances, strength of vertical mixing, and cloud properties were varied within physically plausible ranges. The computer then generated the corresponding spectrum and compared it with the real data. Models that matched one region but failed across many others were rejected. Those capable of explaining the underlying brightness, the overall slope, and several molecular features at the same time were retained for deeper analysis. The resulting effective temperature was close to 564 Kelvin, equivalent to about 291 degrees Celsius, or approximately 556 degrees Fahrenheit. Effective temperature does not mean that every part of the atmosphere is at exactly that temperature. The deeper layers may be hotter, while the upper regions may be cooler. It is a combined value describing the amount of energy the object radiates into space, much like representing an atmosphere with many temperature layers by one overall number. A temperature near 291 degrees Celsius sounds extremely hot by Earth standards, but GJ504b is still considered relatively cool among directly imaged companion objects. Many other young worlds reach temperatures of thousands of degrees, because they formed recently and still retain enormous amounts of heat. GJ 504b has cooled considerably more, yet it continues to emit enough infrared radiation for James Webb to study. This remaining heat is what allows scientists to connect age with mass. A giant gaseous object continuously loses energy after it forms. Over time, it cools and becomes fainter. Lower mass objects generally cool more quickly, while more massive objects have stronger gravity, experience greater compression, and can retain internal heat for longer periods. For the same observed temperature and brightness, a young object may therefore be relatively lightweight, while an old object usually needs to be more massive. Imagine two gaseous spheres cooling over time. The first formed recently and remains hot, even though it is not especially massive. The second has existed for billions of years, but still emits a similar amount of heat. To retain that energy for so long, the second sphere would usually need to contain more material and undergo much stronger compression. This is why the estimated age of the system once created such a large difference in how the mass of GJ 504b was interpreted. When the GJ 504 system was believed to be young, the infrared point of light could be explained by an object only a few times more massive than Jupiter. But if the star and its companion have existed for billions of years, such a low-mass object would have difficulty retaining the temperature now being observed. In that case, GJ 504b would need to be far more massive. The new spectrum helps reduce some of this uncertainty by providing additional information about gravity. The stronger the object's gravity, the more tightly its atmosphere is compressed. At the same altitude, the pressure may be greater, causing molecules to collide more frequently and changing the shapes of some absorption regions. These changes are difficult to detect in a simple infrared image, but they can leave signatures in a sufficiently detailed spectrum. Gravity also affects the vertical extent of the atmosphere. An object with weaker gravity allows gas to spread across a larger region. Under stronger gravity, the atmosphere is held more tightly around the object. This changes how temperature, pressure, and clouds are distributed with depth. When the model must explain both the molecular features and the amount of escaping light, only certain ranges of gravity produce physically reasonable results. The spectrum does not, however, provide a completely independent measurement of gravity. The effects of gravity can become entangled with those of temperature, composition, and clouds. A high cloud layer may conceal regions of greater pressure, making the spectrum resemble that of an atmosphere with a different gravity. Correctly identifying the type of cloud, therefore, becomes especially important. Clouds are not merely one atmospheric detail. They determine which pressure levels and depths are actually being observed. Once the salt cloud layer was included, the team could find a combination of temperature and gravity that fit the full data set more successfully. From the estimated gravity and the size of the object, its mass could then be inferred. The basic principle is fairly simple. Gravity depends on how much matter an object contains and on the distance from its center. If researchers know approximately how large a world is and how strong gravity is within its atmosphere, they can estimate the mass hidden inside. The size of objects like GJ 504b does not increase dramatically with mass. A brown dwarf dozens of times more massive than Jupiter may still have a radius close to Jupiter's. As more material is added, stronger gravity compresses the gas inside more tightly, so the object does not expand in direct proportion to its increasing mass. Simply measuring the size, therefore, cannot reveal whether GJ 504b is a few times or several dozen times more massive than Jupiter. The gravity information encoded in the spectrum is what helps distinguish between those possibilities. The best-fitting combination of models produced a central mass estimate of nearly 25 times the mass of Jupiter. Evolutionary models used to connect the temperature, brightness, and gradual cooling process also gave an approximate range of 19 to 27 Jupiter masses. At the same time, the age of the system was placed at roughly 2.5 to 4 billion years. These numbers should not be understood as perfectly precise and unchanging measurements. They depend on assumptions about the atmosphere, the clouds, the age of the star, and the way the object has cooled since it formed. If some physical process is still missing from the models, or if the cloud type has not been described accurately, the estimated mass range may continue to change. The new results narrow the picture and make a massive object more plausible, but they do not remove every uncertainty. Even so, the difference from the original interpretation is enormous. AGJ 504b, only a few times more massive than Jupiter, would be a relatively lightweight gas giant, although one in an unusually wide orbit. An object approaching 25 Jupiter masses lies much deeper within the region commonly associated with brown dwarfs. Its gravity would be stronger, its cooling history longer, and its formation history potentially different from that of an ordinary planet. But mass alone still cannot deliver the final verdict. A boundary near 13 Jupiter masses is often used as a convenient dividing line because an object above that level may have burned deuterium during the early stages of its existence. Yet the ability to undergo a short-lived reaction does not necessarily reveal how the object was born. An object formed within a disk around a star may exceed this limit, while in some cases an object formed through the contraction of a gas cloud may fall below it. Origin remains a crucial factor. If GJ 504b formed by accumulating material within the disk of gas and dust surrounding its star, it could be considered an extremely massive planet. If it formed through the collapse of a region of gas, in a process more similar to the birth of a small star, the term brown dwarf would be more appropriate. Mass tells us where the object lies on a scale of size and gravity, but it does not directly preserve a record of how it formed. The wide orbit does not settle the question either. The large separation may suggest a formation process more similar to that of a brown dwarf, because creating an extremely massive planet far from its star is difficult. But a planet could also have formed closer in and later been pushed outward through gravitational interactions. An unusually large disk of material might also have allowed such an object to form at a wide distance. Each possibility requires additional evidence. This is where chemical composition becomes important. An object that formed directly from the same gas cloud as its host star may preserve elemental ratios relatively close to those of the star. A planet formed within a disk, by contrast, may gather additional ice, dust, and solid material, enriching its atmosphere in elements heavier than hydrogen and helium. The spectrum is therefore useful for more than measuring temperature or detecting clouds. It may also preserve traces of the environment in which GJ 504b was born. Salt clouds once again affect this process. If clouds conceal atmospheric layers containing many molecules, the abundances of carbon, oxygen, or sulfur may be estimated incorrectly. When the appropriate cloud layer is included, the research team can evaluate the chemical composition without compensating with unrealistic elemental ratios. This allows the question of origin to be examined on a more reliable foundation. GJ 504b has therefore undergone a major transformation in the way humanity understands it. It began as a young, lightweight pink planet. Later, studies of the star's age drew attention to the possibility of an older and more massive object. The James Webb spectrum, together with models that include vertical mixing and salt clouds, has now moved the estimated mass closer to 25 times that of Jupiter. This result makes GJ 504b look more like a brown dwarf than it did before. But it does not completely end the debate. The mass estimate still depends on models, and the object's formation process has never been observed directly. Nature may have produced an unusually massive planet, or a relatively lightweight brown dwarf, and those two possibilities could result in atmospheric appearances that look very similar today. Its mass pulls GJ 504b toward the brown dwarf region. Yet within its chemical composition, one clue remains that may tilt the story in another direction. A mass close to 25 times that of Jupiter makes GJ 504b look more like a brown dwarf than an ordinary gas giant. But mass tells us only how much material the object contains today. It does not directly reveal how the object was born. To search for traces of its past, researchers must return to the spectrum and examine how the elements in its atmosphere compare with those in the host star. In astronomy, the word metal is used more broadly than it is in everyday life. It does not refer only to iron, copper, or shiny solid materials. Nearly every element heavier than hydrogen and helium can be grouped under the name metals. Carbon and methane, oxygen and water vapor, nitrogen and ammonia, and sulfur and hydrogen sulfide are all considered metals in astronomical language. Hydrogen and helium make up most of the matter in stars and giant gaseous planets. Heavier elements usually account for only a small fraction, but their proportions may preserve information about where and how an object formed. When researchers describe an atmosphere as metal-rich, they do not mean that it contains enormous blocks of solid metal. They simply mean that carbon, oxygen, nitrogen, sulfur, and other heavy elements are more abundant than in the reference composition being used. For GJ504b, the most important reference is the composition of the star GJ504. The star and its companion are believed to have formed from the same original environment. If both were born through the direct contraction of different parts of the same gas cloud, their overall compositions might remain relatively similar. The smaller object could still undergo certain changes, but it would generally be expected to preserve many of the chemical characteristics of the material that formed the star. This is the scenario most closely associated with the formation of a brown dwarf. A sufficiently dense region of gas begins collapsing under its own gravity. Material continues falling toward the center, raising the temperature and pressure. If the final mass becomes high enough, a star is born and begins sustaining hydrogen fusion. If the collapsing region does not gather enough material, it may become a brown dwarf, still hot and bright in infrared light, but unable to shine steadily like a true star. In this scenario, the object forms mainly from gas in the original environment. Its composition may therefore remain fairly close to that of its stellar companion. This does not mean that the two objects must be completely identical. Real formation processes are more complicated than simple models, and elements may not be distributed evenly. Even so, chemical similarity remains one of the clues considered when evaluating whether an object formed in a star-like way. Planet formation follows a different path. When a young star is born, it is often surrounded by a disk of gas, dust, and small particles. Within that disk, particles collide and stick together, gradually building larger structures. In regions cold enough, water and other volatile compounds can freeze, increasing the amount of solid material. Large cores made from rock, ice, and dust may then attract enormous quantities of hydrogen and helium gas, growing into giant planets. A planet formed in this way does not collect only gas. It also accumulates solid material rich in carbon, oxygen, and other heavy elements. As a result, the proportion of heavy elements in the planet may become greater than the corresponding proportion in the host star. The degree of enrichment depends on where the planet formed, how much gas and solid material it acquired, and whether it migrated through the disk during its early history. The solar system provides a familiar example. Jupiter and Saturn are composed mainly of hydrogen and helium. This is understood as a trace of the way the planets accumulated both gas and solid material from the disk surrounding the young Sunday. However, no single ratio applies to every planet. Each star system develops under different conditions, and formation histories often unfold through several stages. For GJ504b, the James Webb Spectrum allowed the research team to estimate the abundances of several elements in the atmosphere. The results suggest that the object may be richer in carbon than its host star. Oxygen also appears to be enriched, although the amount depends more strongly on the atmospheric model and the influence of clouds. Sulfur, meanwhile, seems closer to the proportion found in the star. The differences among these elements are significant. If the atmosphere simply copied the composition of the star, carbon, oxygen, and sulfur might be expected to vary in a more similar way. The apparent enrichment of carbon, and possibly oxygen, without a corresponding increase in sulfur suggests that the object may have accumulated material through a selective process. Such a process can occur within the disk surrounding a young star, where different compounds freeze, evaporate, or become distributed unevenly according to distance and temperature. The spectrum does not allow researchers to look directly back at the disk that existed billions of years ago. They can only observe the atmosphere as it is today and use its composition to infer the past. This process contains several layers of uncertainty. The atmosphere may have changed over time. Some elements may lie deeper than the current spectrum can probe. Clouds may conceal regions containing important molecules. Vertical mixing may also carry material from other depths into the observable layers. This is why the salt cloud layer identified earlier has a direct effect on the question of origin. If a model does not include clouds, it may interpret weak water vapor or methane signatures as evidence that oxygen or carbon is scarce. But those signatures may also be weak because clouds are blocking some of the light from regions containing those molecules. Once the clouds are placed correctly in the model, the amount of each element required to produce the spectrum may change. In other words, before chemistry can be used to read the history of formation, researchers must first understand how the atmosphere has filtered the light. An error in the cloud model can lead to an incorrect estimate of carbon or oxygen, which can then alter the conclusion about whether GJ504b formed more like a planet or a brown dwarf. Clouds do not merely conceal the deeper layers. If they are described incorrectly, they can also conceal the story of the past. The new study attempted to consider temperature, gravity, chemical mixing, and clouds at the same time. With a more complete model, the apparent enrichment of carbon became especially noteworthy. This clue favors the possibility that GJ504b formed within the disk of material surrounding its star, gathering both gas and material rich in heavy elements. Under this interpretation, it may be a planet formed through a process similar to that of giant planets, but one that grew to an unusually large mass. This possibility is not easy to explain completely. GJ504b currently lies very far from its host star. At such a wide distance, the material in the disk would usually have been less dense, and the time required to build a large core may have exceeded the lifetime of the gas disk itself. If the object formed like a planet, it may have been born somewhere else and later moved outward. The disk around GJ504 may also have been larger and more massive than the disks usually imagined. Another possibility is that part of the disk collapsed under its own gravity, allowing the object to form more quickly than through the ordinary process of gradual core growth. These scenarios are not completely separate paths that can never overlap. An object may form inside a disk through rapid gravitational collapse, giving the process some features similar to star formation. It may also exchange material with the disk after it forms, causing its present atmosphere to differ from its original composition. The labels, planet and brown dwarf, can therefore hide a formation history that is more complicated than either name suggests. Elemental enrichment is not absolute proof either. A brown dwarf formed from a collapsing gas cloud may still experience processes that make its atmosphere chemically different from its star. Conversely, a very massive planet may acquire most of its mass from gas and become only slightly enriched. The observed composition also depends on whether the atmosphere represents the entire object or only the outer layers accessible to the spectrum. The research team also identified subtler variations within the same molecule related to different isotopes of carbon monoxide. Isotopes are versions of the same element with slightly different masses. Their ratios can sometimes carry information about the source of the material or the chemical processes involved. For GJ504b, however, the meaning of these measurements still requires further testing. The data shows that the spectrum has reached an impressive level of detail, but those small differences should not yet be used to construct an overly certain formation story. The most honest answer, therefore, lies somewhere between the two classifications. The new mass estimate moves GJ504b toward the brown dwarf region. Its carbon-rich and possibly oxygen-rich composition, however, supports a formation process more similar to that of a planet. The wide orbit creates difficulties for conventional planet formation models, but it does not rule out the possibility that the object changed position in the past. No single piece of evidence is strong enough to decide the entire story. What the new study provides is not a final label, but a better collection of clues. GJ504b may have formed within the disk around its star and accumulated substantial amounts of heavy elements. It may also have been born through a more rapid collapse process closer to the way brown dwarfs form. Its present chemical composition makes the first possibility more compelling than before, but not strong enough to eliminate the second. This helps explain why researchers remain cautious when naming the object. Pink planet is still the most memorable description. Brown dwarf fits the new mass range more closely. Substellar companion avoids making a firm claim about its origin. Each name emphasizes a different part of the evidence, while GJ504b remains near a boundary that nature may not divide as clearly as human classification systems do. Perhaps the important question is no longer which category GJ504b must be placed into immediately. Its value lies in forcing formation models to explain several characteristics at once: its large mass, wide orbit, relatively low temperature, chemically disequilibrated atmosphere, enriched composition, and the salt clouds obscuring its deeper layers. A successful explanation must fit all of those clues, not only one isolated number. From infrared light, astronomers move from a point of light to chemical composition, from composition to atmospheric motion, and then from the elements present today back toward the environment in which the object formed billions of years ago. That journey has not produced an absolute conclusion, but it shows that light can preserve the past far longer than the material structures that originally shaped it. GJ504b may be an exceptionally massive planet. It may also be a brown dwarf that formed in a way unlike more familiar examples. The new study makes the planet-like scenario more convincing than it was before, but the boundary remains open. And perhaps the most important question is not what we ultimately call this object, but what its clouds are warning us about. Many other worlds may also have been interpreted incorrectly. GJ504b is still only one object among the many giant gas planets and brown dwarfs that have been discovered. The salt clouds inferred from its spectrum do not transform the whole field of astronomy, nor are they enough to force every current atmospheric model to be rewritten. But this case reveals something more important and more practical. When studying a world at a great distance, the way clouds are described can influence nearly every conclusion drawn from its light. GJ504b has become a valuable test case because it is much cooler than many of the young objects commonly observed through direct imaging. Newly formed gas giants still retain large amounts of heat, so they shine strongly in the infrared and are relatively easier to detect. Their high temperatures also produce cloud types formed from heat-resistant compounds. As an object cools, substances that can remain gaseous in deeper layers begin to condense at different altitudes. The composition of its clouds, therefore, does not remain unchanged throughout the life of the world. A very hot atmosphere may contain cloud particles formed from materials associated with rock or heat-resistant metals. As the temperature falls, those clouds may sink into deeper regions, disappear from the layers probed by the spectrum, or be replaced by compounds that condense at lower temperatures. GJ504b lies within a temperature range where familiar cloud types from hotter objects are no longer necessarily the best choice. The models must consider different particles, including salt compounds. This explains why a model that works well for a hot world cannot always be transferred to a cooler object without modification. The physical laws remain the same, but matter may exist in different states. Just as water vapor, liquid water, and ice are all made from the same molecule but appear under different conditions, compounds in distant atmospheres can also change from vapor into cloud particles as temperature and pressure shift. If a model uses the wrong kind of cloud, the error affects far more than our imagined picture of the object's sky. It spreads through the entire interpretation of the spectrum. A cloud layer that is too transparent allows the model to see more deeply than the real atmosphere permits, collecting too much light from hot regions below. A cloud layer that is too thick conceals molecular features that the telescope still detects. Clouds placed too high or too low also change which atmospheric layers contribute to each wavelength. If the underlying brightness is misunderstood, the temperature may be adjusted incorrectly to compensate. If a cloud weakens a molecular signature, but the model lacks the appropriate cloud layer, researchers may conclude that the molecule is less abundant than it truly is. From the molecular abundances, the proportions of carbon, oxygen, or sulfur may also be inferred incorrectly. Those proportions are then used to evaluate whether the object formed more like a planet or more like a brown dwarf. Gravity is also affected indirectly. The shapes of certain absorption regions depend on pressure, and pressure is related to gravity. But if clouds conceal atmospheric layers with higher pressure, the spectrum may appear different from that of a transparent atmosphere. An incorrect gravity estimate changes the inferred mass. That mass is then combined with brightness and temperature to estimate the object's age and cooling history. An incomplete assumption about clouds can therefore begin with a layer of extremely small particles and end with an entirely different formation story. The object may be judged lighter or heavier. It may be described as younger or older. Its atmospheric composition may appear closer to that of the host star or more enriched in heavy elements. The same spectrum can then lead to two different interpretations of the object's origin. GJ 504b shows that these parameters should not be read separately. Temperature, chemical composition, mixing, clouds, gravity, mass, and age are all connected. Changing one part of the model can cause several others to shift. A reasonable result must do more than produce a spectral curve that resembles the data. It must also describe an atmosphere that can physically exist, with molecules, temperatures, and cloud particles that are consistent with one another. James Webb's role in this story is not to provide a clearer image of a surface. No solid surface has been seen on GJ 504b, and the telescope still cannot resolve individual cloud bands. Its advantage lies in its ability to collect a spectrum from an object that was previously too faint for detailed ground-based measurements. Infrared regions absorbed by Earth's atmosphere can be observed from space, while the instrument's sensitivity allows subtle features to separate instead of blending completely together. This opens the possibility of studying a wider group of objects. In the past, direct spectra were generally easier to obtain from young, hot, and bright gas giants. Cooler objects, closer to the mature states of giant planets, emit less light and are therefore more difficult to investigate. GJ 504b shows that at least part of this gap is now beginning to come within reach. As more cool gas giants and brown dwarfs are observed using the same methods, astronomers will be able to compare how clouds change with temperature and gravity. They can test whether salt clouds commonly appear within a particular temperature range or become prominent only in objects with certain compositions. They can also examine how vertical mixing changes as an object cools and which molecules begin to dominate. A single object can always contain unusual characteristics, but when the same signature appears across several worlds, researchers can begin to identify a general pattern. Conversely, if GJ 504b differs clearly from other objects at similar temperatures, that difference will also be valuable. It may show that the object's original composition, gravity, or formation history matters more than temperature alone. Future observations may extend the spectrum into other wavelength regions. Each part of the light probes the atmosphere in a different way. Some wavelengths are more sensitive to higher layers, while others may receive light from deeper regions if the clouds are not completely opaque. When several parts of the spectrum are combined, cloud models will have to explain a much larger body of data at the same time, making it more difficult to produce a match through arbitrary adjustments. Researchers may also test additional types of cloud particles. The current model shows that salt clouds fit the data better than the alternatives that were examined. But this does not mean every detail of the cloud layer has been determined. The real atmosphere may contain several kinds of particles. Their sizes may change with altitude, and the clouds may not cover the entire object evenly. More complex models can be tested once the data becomes precise enough to distinguish among them. The composition of GJ504b must also be compared more accurately with that of its host star. The star serves as a reference for the original material in the system. If the abundances of carbon, oxygen, and sulfur in the star can be measured more precisely, the degree of enrichment in the companion can also be determined with greater confidence. This may help researchers evaluate whether the atmosphere of GJ504b accumulated large amounts of solid material from the disk, or preserved a composition closer to that of the original gas cloud. Another direction is to observe the object at multiple points in time. If GJ504b rotates and has unevenly distributed cloud regions, its brightness or spectral shape may change slightly as different areas turn toward Earth. If detected, such variations could provide clues about how the clouds are distributed, but the current data does not support the claim that a definite cloud map can be produced. The signal may be too small, the rotation period may be difficult to determine, and several other effects could create similar variations. Even if the spectrum changes over time, turning those changes into a map would still be an indirect process. James Webb would not see individual clouds moving across a clearly resolved globe. Researchers would have to infer their distribution from the way the light rises and falls as the object rotates. The result might show that the atmosphere is uneven, but it would not necessarily reveal the exact shape of each region. That caution is essential. In astronomy, the data often contains less direct information than scientific illustrations make us feel it does. A spectrum may hold many signatures, but every conclusion still depends on how thoroughly other possibilities have been tested. The best model available today is not the final answer. It is the explanation that fits the current data and physical understanding most successfully. For GJ504b, the path toward salt clouds can be summarized without adding any imagined imagery. First, James Webb collected the object's own light and spread it into a spectrum. Within that spectrum, researchers identified the signatures of several molecules. They created simulated atmospheres with different temperatures, gravities, and compositions, then compared the results with the data. Cloud-free models explained part of the spectrum, but allowed too much light to escape from deeper layers. Once an appropriate cloud layer was added, both the underlying brightness and several absorption regions moved closer to the observations. That is the basis of the conclusion. No one has seen individual salt particles. There is no direct image showing the shape of the cloud layer. There is no map revealing where the clouds are concentrated. These clouds were identified through the effects they left in the light. When they were excluded from the models, the spectrum was difficult to explain in terms of both brightness and composition at the same time. Once they were included, the physical picture became more consistent. The indirect nature of the evidence does not make it less valuable. Most of what humanity knows about worlds beyond the solar system has been built in a similar way. No instrument has ever been placed inside their atmospheres. Light is the only connection between those objects and our telescopes. The task of science is to determine which physical processes could have produced the observed light, and then test whether that explanation continues to hold as new data becomes available. GJ504b reminds us that light tells us not only what is present, but also what is hidden. A molecule leaves its mark by absorbing certain wavelengths. A cloud layer changes the depth from which light can escape. Mixing carries molecules upward from deeper regions. Gravity compresses the atmosphere and influences pressure. All of these effects combine to create a single spectral curve. A cloud, therefore, does more than conceal what lies beneath it. In astronomy, it also helps determine the story that light is able to tell. If the cloud layer is understood correctly, the hidden atmospheric regions behind it can still be inferred with care. If it is overlooked, the temperature, composition, mass, and even the formation history may all be interpreted differently. The broader significance of GJ 504b lies in this quiet warning. Other cool and faint worlds may also contain cloud types that were not fully represented in early models. Some molecules may have been underestimated because their signals were partially hidden. Some objects may have been assigned inaccurate temperatures or gravities because the appropriate cloud layer was not included. This does not prove that every previous result was wrong. It simply shows that each temperature range must be studied using cloud types that could actually exist under those conditions. As more spectra are collected, these models will continue to be tested. In some cases, salt clouds may explain the data well. In others, a different kind of particle may provide a better fit. Some objects may require almost no thick cloud layer at all to explain their light. The differences among them will help make the larger picture of giant atmospheres more accurate. GJ 504b does not provide a final answer about the boundary between planets and brown dwarfs, nor has it fully revealed the structure of its clouds or the exact location where it formed. But it has shown that a faint point of light can contain enough information to test several layers of physics at once, from molecules and atmospheric motion to condensation, gravity, and cooling across billions of years. From nearly 60 light-years away, GJ 504b remains only a tiny point. But that tiny point is no longer completely silent. At the beginning of the story, GJ 504b appeared as a pinkish-purple sphere drifting through space. In artistic illustrations, that world had a clearly defined circular outline, bands of clouds stretching around its atmosphere, and regions of light and darkness that made it seem far more familiar than its true distance would suggest. Looking at such an image, it is easy to feel that humanity has already observed a complete planet, seen its color, and discovered what lies beneath its clouds. But the real data is far more modest. There is no sharply defined sphere, no horizon, no cloud bands that can be pointed out in an image. GJ 504b remains only a tiny point of light beside the much brighter glow of its host star. When James Webb separated that point into a spectrum, what appeared was not a new photograph. It was simply a rising and falling line, with some regions where the light was stronger and others where it had been reduced. Yet within those missing portions of light, the atmosphere began to reveal its story. Some wavelengths had been absorbed by water vapor. Other regions carried the signatures of methane, carbon monoxide, carbon dioxide, and ammonia. Hydrogen sulfide, along with subtle variations within certain molecules, showed that the spectrum had become detailed enough for scientists to recognize differences that had blended together in earlier observations. No molecule appeared as a name already written into the data. Researchers had to compare the entire spectrum with measurements made in laboratories and then test many different simulated atmospheres. They changed the temperature, gravity, composition, and strength of mixing between atmospheric layers. Every time one assumption was adjusted, the entire spectrum had to be examined again, because a change that improved the fit in one region could make another region more difficult to explain. From the simultaneous presence of methane, carbon monoxide, and ammonia, they recognized that the atmosphere was not completely still. Material may be carried upward from hotter, deeper layers before chemical reactions have enough time to bring everything into a stable state. The observed molecules, therefore, reflect more than the conditions where the light finally escapes. They also preserve traces of the journey taken by the gas. But that mixing still could not explain the entire spectrum. Cloud-free models allowed too much light to escape from the deeper layers. Some molecular features became stronger than those observed by James Webb, while the object's overall brightness also failed to match completely. The missing component did not appear to be another gas with its own distinct fingerprint. It was a layer of material that dimmed several regions of light at once. When salt compounds were allowed to condense into tiny particles within the atmosphere, the models began to move closer to the data. The cloud layer blocked some of the radiation from deeper and hotter regions, reducing the brightness at the appropriate wavelengths while weakening certain molecular features until they more closely resembled the observations. Humanity has not seen those clouds directly. No image shows whether they wrap around GJ 504b in broad bands or gather in separate regions. We do not know what color they are, how thick they may be, or how they change as the object rotates. Their presence is inferred from something more basic. Without salt clouds, the light is extremely difficult to explain in terms of both brightness and composition at the same time. Once the cloud layer is included, the physical picture becomes more reasonable. The same spectrum also changed the way the entire object is understood. GJ 504b may not be a young planet only a few times more massive than Jupiter, as the earliest estimates suggested. Its temperature, gravity, and cooling history indicate that it may have existed for billions of years and may carry nearly 25 times the mass of Jupiter. That places it close to the region commonly associated with brown dwarfs. But the chemical composition does not close the story entirely in that direction. The apparent enrichment of carbon, and possibly oxygen, relative to the host star suggests that the object may have accumulated additional heavy elements within the disk of gas and dust surrounding the young star, a process closer to the way giant planets form. Its mass makes GJ 504b resemble a brown dwarf. Its composition leaves open the possibility that it is an exceptionally massive planet. And so, even after all the new observations, the final answer remains incomplete. We still do not know whether GJ 504b was born from a solid core that gathered gas within the disk around its star, or from a region of gas that collapsed under its own gravity like a very small star. We do not know whether salt clouds cover most of the atmosphere, or are concentrated only in certain areas. We do not know whether those cloud layers remain stable for long periods or continually change as material moves between atmospheric depths. Nor do we know how many other cool and faint worlds may be hiding cloud types that current models do not yet describe correctly. The unanswered questions do not weaken the discovery. They reveal the boundary between what has been measured and what is still being inferred. Science does not need to turn every point of light into a complete story immediately. Sometimes the greatest value of an observation lies in showing what an older model was missing, and where the next question should be asked. The pink image made GJ 504b easy to remember. But the true significance of this world does not lie in its reconstructed color or the cloud bands of an illustration. It lies in the fact that a very small amount of light has now been read more carefully than before. Each absorption region suggests which molecules may be present. The unbalanced proportions reveal movement between atmospheric layers. The dimmed light points toward a cloud layer that has never been seen directly. And the overall shape of the spectrum allows researchers to reconsider the object's age, mass, and origin. Sometimes a major advance does not come from discovering another new world. It comes from returning to a familiar point of light and realizing that its signal was not interpreted accurately enough the first time. A missing cloud layer can lead to the wrong temperature, alter the apparent chemistry, and send the formation story in a different direction. When that cloud is finally included, the world itself does not change. Only the human understanding of it moves closer to reality. That is also the lasting message of GJ 504b. The universe rarely gives us complete pictures. Most of the time, it sends only faint, limited signals that have already been transformed along the way. Knowledge does not emerge by filling the gaps with imagination, but by patiently distinguishing what the light truly reveals from what a model is attempting to explain. An incomplete answer is not the end of understanding. It is a sign that humanity has come close enough to recognize the limits of the previous answer. And sometimes, the moment we realize that we are missing a cloud layer, a process, or a new assumption, is the very moment science takes another step forward. GJ 504b remains where it has always been, nearly 60 light-years away, far from the sun and far beyond the reach of any instrument humanity can currently send to it. It offers no clear image of its atmospheric layers. It sends only a small, faint, and incomplete amount of light. Yet, within the light that remains, humanity has begun to recognize water vapor, methane, movement between atmospheric layers, and a layer of salt clouds that may have concealed the deeper parts of that world for billions of years. From Earth, it is still only a point of light. But sometimes, a point of light is all we need to begin understanding a world.